All right, class, this is the 10A sample exercises, so let's take a look at this. So for the first one, first of all, you should know that this is at the top of page 403 in the white chemistry book. And it says, in the countries that use the metric system, such as Canada, atmospheric pressure and weather reports is given in units of kPa, that's kilopascals. Convert a pressure of 745 torr to kPa. An English unit of pressure sometimes used in engineering is, so let's start with A first, when we're just converting a pressure of 745 torr to kPa. I'm going to put that over 1. This is how I do all of my conversions. Now, we should know that 760 torr is equal to 1 atmosphere. 1 atmosphere is also equal to 101.3 kPa. Okay, that information is in the book, and that's all part of our conversion. So what we're going to have to do then is divide by 760 and multiply by 101.3. What that gives us then, when we get to 101.3, that'll give us 99.3 kPa. All right? So that means my torr cancels with torr, and what I'm left with then is in kPa. So I multiply the two on top and divide by the one on the bottom. That's it, just a simple conversion. This next one says, English unit of pressure, sometimes used in engineering, is pounds per square inch, or PSI. So 1 atmosphere equals 14.7 pounds per square inch if a pressure is reported as 91.5, so that's going to be 91.5 PSI over 1. I always do the same thing. Now what's my conversion? My conversion is 1 atmosphere. That goes on top because that's what I'm looking for. And then pounds per square inch goes on the bottom, 14.7 pounds per square inch. So all I have to do then is divide 91.5 by 14.7, and what we should get then is something very close to 6.22 atmospheres. Notice I'm rounding off to 1, 2, 3 significant figures. We haven't done calculations like this in a long time, and I round off to 3 significant figures because that's what I start with for the problem. Up here, 1, 2, 3, 1, 2, 3 significant figures because that's what I start with for the problem. Moving on. We're here at 10.4 using the ideal gas law equation. Now the ideal gas law equation, let me get there. 10.4 is at the top of page 410. First thing we know about the ideal gas law equation is pressure times volume equals the number of moles times the R value, which is the gas law constant, times temperature. Now here's what we know. We know that pressure, okay, can be in atmospheres, it can be in torr, it can be in kPa. Volume is always going to be in liters. Number of moles, N is in moles. The R value depends on the pressure. And we'll get into what that is when we get there. T, temperature, is always in Kelvin. Okay, so that gives us some idea of what we're working with. PV equals nRT. So I have to change now. Well, here's what I'm going to do. If I have, for instance, the volume here is in 250 milliliter flask. So that's going to be, first of all, what are we looking for? A sample of CaCO3 is decomposed. Carbon dioxide is collected at 250. After the decomposition is complete, the gas has a pressure of 1.3 atmospheres. How many moles? So I'm looking for the number of moles. So what I do is I divide both sides by RT, like this, and I get N equals PV divided by RT. Once I get to that point there, I start to plug in the information that I have. My pressure is 1.3 atmospheres. Okay, my volume is 250 milliliters, which equals 0.25 liters. 0.25 liters, like that. All divided by the R value, 0.0821. If we're talking about atmospheres, that's liters per atmosphere over mole Kelvin. That's my R value. The temperature is given to us in 31 degrees Celsius plus 273. So that gives me a temperature of 304 Kelvin, like that. So what I'm working on here then is I'm going to be multiplying and dividing to get a total, the 1.3 times 0.25 divided by the 0.0821, and then divided by 304 Kelvin. That gives me a total of 0.013 moles of CO2. Notice that the atmospheres on top here cancels with the atmospheres on top of the R value. Liters on top of the whole fraction, it cancels with the liters on top of the R value. Moles is left on the bottom, and Kelvin is canceled with Kelvin. So what I end up with then is like a 1 over moles. And that equals just straight up moles, like that. Okay, that's a good exercise of how to use the PV equals nRT. The toughest part there is definitely the figuring out what R value to use and then doing the math to solve for your number of moles. All right, I'm going to stop there, and we'll pick up for the second half.